group, and I hope this new group will encourage and support young mathematicians in Korea to achieve top level results, and also have some bridge between world-class experts with Korean mathematicians, or mathematicians in Korea, let's say, to be correct. And also I'm very happy to give a talk here on a very recent work on random subgraphs of the hypercube. The talk will be based on joint work with Joshua Erde at TU Graz and Michael Krivelevich at Tel Aviv University. And in the talk, I will first briefly discuss or present some classical results on a random subgraph of the hypercube. Of course, I will have to define what do I mean by this hypercube. And then I will focus on the so-called giant component in the supercritical regime, and also discuss some expansion properties and consequences, together with some proof ideas. And I will conclude the talk with some proof ideas. And if you have any questions, you can ask me in the middle of the talk as well. So the first part, let me define the model. What do I mean by the hypercube? It's given integer d, usually large integer. We will consider the d-dimensional hypercube QD, which is a graph, which we will consider as the graph with vertex set given by binary strings of length d. So hopefully you will be able to see my mouse, as d will indicate the dimension as well as the length of the binary string. So each vertex consists of 0, 0, 1, 1, 1, and so on of length d. And the edge set consists of unordered pairs of two binary strings of length d, and there is an edge between them if they differ exactly in one coordinate. And then very easy to see is that the number of vertices will just be 2 to the d. And also, due to the definition of our hypercube, it's always d-regular. So every vertex is connected to exactly d neighbors. And therefore, the number of edges is also given. And perhaps it's good to have some visualization. And indeed, the hypercube can be, the dimensional hypercube can be seen through a Hasse diagram of partial orders given by subset relations, such as if you have d equals 4, then 0, 0, 0 will be connected to, obviously, when there is exactly one in one coordinate, and so on. So this is so-called Hasse diagram. Very classical, very well known. And what we want to study is the so-called bond population. Namely, what we do is the following. Given a probability, edge probability p between 0 and 1, we will retain each edge of the hypercube independently with the probability p. Here I indicate by red edges, which we keep. Otherwise, with the probability 1 minus p, of course, we do not keep the edge. So this is like visualization when I simulated just by hand by putting p equals 1/2, and perhaps this can be seen. Maybe exactly 2 neighbors are there, maybe not exactly, but on average, I wanted to keep 2 edges. 2 neighboring edges, I mean, for each vertex. I think hopefully this visualizes it nicely. And this is so-called bond population. As you can imagine, if p is small, then the subgraph, we call also the subgraph, random subgraph, indeed, in a bigger context, or bond population. As you can imagine, if as the edge probability p increases from 0 to 1, the graph becomes sparser to the denser. So so we are interested in so-called critical or phase transition phenomenon, or the so-called threshold phenomenon for certain properties of a graph. One of the basic properties of a graph is being connected. And indeed, it was Shapochenko and Botian already in 60s. They studied the so-called connectedness, for which probability P is the random subgraph QDP is connected. And this indeed corresponds to the nice classical population theory that in two-dimensional lattice, the population threshold is 1/2. It does correspond nicely, and indeed it can be proved rigorously. And also there are strengthenings and also extensions by Adolph and Spencer and later by Bolobach. And they show that indeed probability, edge probability P is equal to 1/2 is the so-called sharp threshold for the connectedness. More precisely, what we mean by that, the sharp threshold is that for any given positive integer epsilon, the probability that a random subgraph of the hypercube QDP is connected tends to either 1 or 0. So it tends to 0 if P, for any P which is smaller than 1 minus epsilon over 2, as D tends to infinity. Remember throughout the talk, the D will tend to infinity, and therefore the number of vertices 2 to the D will also tend to infinity. So you can think of it either way, but let's say D tends to infinity. On the other hand, if P is at least 1 plus epsilon over 2, then for any such P, the probability that a random subgraph QDP is connected tends to 1. So it's a so-called sharp threshold phenomenon. Having seen such a result, and if you know some classical results on random graphs, it is also very natural to ask also whether P equals 1/2 is also the threshold for perfect matching or some related objects that we know well. And indeed, it is the case. The perfect matching for the perfect matching, so P equals 1/2 is also a sharp threshold for the existence of a perfect matching. And then it's kind of not intuitive in terms of the Erde-Shreni random graph, but it has long been conjectured that P is equal to 1/2 is also threshold for the existence of Hamiltonicity, existence of the Hamiltonian cycle. As I said, for Erde-Shreni, of course, depends on where you see, so how sharp you want to go. It's arguable. But anyway, it was conjectured already in the 80s and has been posed as an open problem in the ICM proceedings of Alan Fries, as well as Daniela Kuhn and Derek Ostus. And indeed, Gondon and his authors could prove that indeed, because 1/2 is a sharp threshold for the existence of Hamilton cycle. This is indeed a very, very deep result. And interestingly, during the last couple of years, this random subgraph of the hypercube attracted the simultaneous attention by different groups of researchers. And indeed, we are one of the groups. And having these results, another very classical question that can be asked in view of the well-known results about the component structure of the random graph is the following: whether the component structure of a random subgraph of the hypercube QDP undergoes a phase transition when P is equal to 1 over D. Why such a thing is natural is that in view of the so-called universality principle of the population theory, which says that the critical threshold for the appearance of the giant cluster, let's say, depends only on the local structure, in particular, the average degree of a random vertex being equal to 1. And it has to do with the so-called coupling with the branching processes. And if the average number of children, let's say, in terms of the branching process, if the average number of children of each vertex is about 1, then we know that there is a transition. Indeed, in hypercube, we know that d-dimensional hypercube is a d regular. So every vertex has the d neighbors, but then we populate, we cap those edges with probability p. Therefore, the average number of edges of an arbitrary vertex will be p times d, and therefore the threshold should be p times d is equal to 1. And indeed, it has been conjectured already in the late 70s, and then it was immediately proved by Erde, Komnosh, and Semeredi. And what they prove is that p is equal to 1 over d is indeed a sharp threshold for the appearance of the so-called giant component. Just make sure that everybody is on the same ground. Of course, this is really classical statement, but nevertheless, I will read it. Yeah. In terms of the emergence of the or appearance of the giant component or the phase transition in terms of the component structure, it goes follows. Yeah, for any epsilon with high probability, meaning that with a probability tending to 1 as d tends to infinity, every component in a random subgraph QDP is small, is logarithmic order in terms of the number of vertices. In other words, it's of order big O of d. Yeah. Remember, the number of total universe consists of 2 to the d vertices. If p is smaller than 1 over d. On the other hand, if we take p to be larger than 1 plus epsilon over d, it's a little bit larger than 1 over d, or for any p which is larger than 1 over d, then there is a unique largest component of linear order, namely order of 2 to the d, while every other component is small. It also lies in this universality class of component structure. And of course, having such a result that d is equal to 1/2 is a threshold, there are other related results when p is close to 1. And this result has been strengthened in many ways when p tends to 1 over d. Not only that, also the other detail, the component structure, and so on. And also only recently we know the correct width of the critical window, even by Nachemias and others. Yeah. On the other hand, in this talk, I will focus mainly on the so-called supercritical regime, namely on this second statement part, when p is larger than 1 over d, and what kind of questions we want to ask. So as I said, I will focus on this so-called supercritical regime, where we have a unique largest component of linear order, the rest is small, and we call such a component a giant component. So we will study what kind of typical properties does this giant component enjoy. For example, one question asked already by Bolobash, Koyakawa, and Uchak in early 90s is that what is the diameter of the largest component, which I will denote by L1. How big is it, or how small it is? Another question that has been asked in the context of the random walk is what is the mixing time of the so-called lazy simple random walk? Why lazy? Because hypercube QD is bipartite. Therefore, we have to always make sure that it stays there at the same vertex, say probably 1/2, and each vertex moves to one of its neighbor chosen uniformly random. So it's so-called the lazy simple random walk. We also learned this random walk terminology already by previous talks in this conference. Another natural question is, where is the length of the longest cycle, the so-called circumference? This is also classical topic studied by Erde, Komnosh, and Erde in the early 80s, even on classical Erde random graph. And then what is the order of the largest complete minor? This is also the classical result on a topic in random graphs, and it's a so-called Hadwiger number. So the order of the largest complete minor, what is the size of the, so how big should be the complete minor? How large can a complete minor could be, which is in L1, and so on and so on. There are many other questions like genus, what would be the genus of the L1, and so on. So there are many questions still open, although the random subgraph of the hypercube is so classical. And then, as I said, there were a lot of studies on this random subgraph in the recent years, and one of them is also done by, two conference organizers, namely Hong and Jae-hoon, who are affiliated at the IBS New Group. They could show that, together with their courses, that indeed in the supercritical regime, there is a cycle of length at least of order 2 to the d divided by some polynomial factor. It's optimal up to this polynomial factor d. So we do expect indeed from in light of the classical result on the longest cycle contained in the giant component by Hadwiger already, we already know that it is linear, and they could show this optimal up to polynomial factor using isoparametric inequality. It's rather classical, but using a new concept, they introduce a new concept, which I like, is also called crux. I hope I'm correct, crux, which measures the smallest, the order of the smallest dense subgraph. Hopefully I'm correct. Jae-hoon and Hong, am I correct? The crux?
Yes, that is correct.
Yeah. So indeed, it's a very nice concept. Indeed, Hong gave a talk in my combinatoric seminar, and it seems to be a very powerful tool to attack many problems. I mean, it's just one corollary indeed. It looks great. It's already a great result, but it's just a corollary of their meta theorem. And Josh Erde and Krivelevich, we can also obtain such a result. Indeed, we can answer all of these 4 problems just using the so-called vertex-expansion property. So it just leads to the second part of the talk, and so let me discuss what it is. We will use the so-called expander, and the expander is such a classical and fundamental concept in many areas, not only in graph theory, discrete math, but it's many, and we have a really extensive introduction to expanders via some very important surveys. Hopefully I name all important people here, and even you see that some of the speakers of this particular conference, like Noga, Nati, and Benny, are main contributors to this area. And let me just recap so that even the PhD student in the room can understand what we are talking about. It's, as I said, it's a very powerful tool, so one has to better to learn once in a lifetime. So given a graph G, we take a subset S. So for any subset, we will let S be a subset of the vertex of the given graph, and we will denote by N of S the external neighborhood of S. Yeah, I visualize it in this fashion. Given a subset of the vertex at S, we are interested in the so-called external neighborhood. Naming the, I just write it here, so I think the picture says everything. So external neighborhood, and we call a graph is an alpha expander if the size of the external neighborhood is at least alpha times the size of S. And this should hold for every subset of the vertex set whose size is at most half of the size of the vertex set. Yeah, for every subset S, you look at its external neighbor, and you have to guarantee. And it is a so-called vertex expansion, and alpha is also called the expansion ratio. And expanders have very, very nice properties and consequences. And the relevant things to our questions are the following. If we can guarantee that our largest component is alpha expander, where expansion ratio alpha is, say, inverse polynomial in D, usually it will be like that, then we can guarantee that such an expander has a small diameter, Of course, it has relation to the expansion ratio, and it does have a long cycle. It does have a larger complete minors and so on. All these consequences you can find one of the surveys, in particular in terms of the graphs, maybe Michael Krivellevich's survey will be very useful. Furthermore, this is for general expanders. And you see the dot, 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 there are other consequences. Furthermore, if our graph G has bounded maximum degree, in particular if it's deregular, if deregular is known to be an expander anyway, then vertex expansion is essentially equivalent to the edge expansion. X expansion can be written with different quantities. One of the quantity which measures edge expansion is the so-called Chiga constant. Chiga constant, we also heard one of the previous talks yesterday. Yeah, so this is of general philosophy, and we want to obtain such an expansion property of the giant component in the supercritical random subgraph. And indeed, we can show that, namely, we let L1, as I said, the largest component in the supercritical regime, then we can show that indeed with the high probability, the largest component is d to the -5 expander. So expansion ratio is 1 over d to the 5. Subject to some constant. There is such a constant, so that blah, blah, blah. So it's about d to the -5 expander. So inverse polynomial in D expander. Indeed, we can say even more. The giant component contains almost spanning subgraph with much better expansion ratio. Yeah, from d to the -5, we can go up to d to the -2, say log d to the -1. Yes, it does have a almost spanning subgraph, which expands even better. And this is indeed very, very good. And as a consequence, and with a little bit of more work, one can show that diameter is big O of d to the 3. Using the meta theorem about the expander has small diameter, usually it will have like d to the 6. The diameter will be just as a direct consequence of that will be, using some meta theorem by many people, will be just d to the 6 diameter will be. But together with that beta expansion, and also one of the ingredients that I will show later, that L1 does have other nice properties, we can indeed improve it, that it does have really small diameter, namely big O of d to the 3rd. And the Chiga constant is d to the -5. As I told you, they are essentially equivalent. So this was the vertex expansion, and this is the edge expansion. They are essentially the same, d to the -5. And it does contain a cycle of length, linear length, up to polynomial factor. Now this polynomial factor is of course given by that expansion, because we can just restrict ourselves to this almost spanning subset, because we are not aiming for the best, the tight length. And also it does contain a complete minor of order d2 to the d over 2. The square root of the number of vertices is kind of optimal value. So t to the d over 2 is the optimal, best possible. But then up to polynomial factor, which is also coming from the expansion ratio. Another classical result on random walk is that the Chiga constant gives the bound, upper bound on the mixing time. I do not want to go into detail, but because it was already mentioned about the mixing time and the random walk, so mixing time of the lazy simple random walk, namely stays the same at the same vertex with probably 1/2, and it goes to one of its uniformly chosen neighbor with equal probabilities, so-called the lazy. And the mixing time is bounded above by the 1 over square of the Chiga constant. Then it will be d to the 10 times the log of the 1 over stationary distribution, which will be of order d, so therefore d to the 11. So everything is now boiled down to prove such a thing, the expansion property. In the remaining part of the talk, I have like, yeah, I will sketch just a simple thing to prove this inverse polynomial expander, namely our target for the following, being a little bit modest, that with a high probability, giant component is 1 over polynomial of D expander. Yeah, so yeah, just to repeat what was written, right? For every subset of the vertex set of the giant, within most half of it, we have to show the size of the external neighbor is at least the size of S divided by poly D. Yeah, this is our target. To prove it, we will use a very standard technique, the so-called sprinkling. We expose the edges into rounds. So we were given probability P, which was 1 over epsilon over D, but we will consider our random subgraph, or we view our random subgraph as the union of 2 independent copies of subgraphs Q1 and Q2, QQ1 and QQ2, where the edge probability Q1, the first one, is chosen very close to P, namely 1 plus delta 1 over D, and Q2 will be quite small, D delta 2 over D, such that 1 minus P, the non-edge probability, 1 minus P is equal to 1 minus Q1 times 1 minus Q2, non-edge probability of the first, non-edge probability of the second. Yeah, so. And we usually, as usual, take delta 2 is much, much smaller than delta 1. This is very standard, so-called sprinkling. It's very powerful when you study random structures. Then, of course, there will be interplay between the graph before sprinkling and after sprinkling. One of the very basic result is the following. Due to anti-convolution similarity, if we denote L1 prime to be the largest component in the first random graph before sprinkling, and L1 is basically before the largest component in the original, or our target, the random subgraph after sprinkling, then using coupling with the branching process with offspring distribution Poisson, 1 plus delta 1 or 1 plus epsilon, we can determine the order of the largest component in both cases. It is a consequence of anti-convolution similarity. It kind of confirms that the critical behavior really depends only on the local behavior, namely number of children. So this is good, classical. But there are 2 other, this will be used, of course, in the proof, but there are 2 other main ingredients to derive the expansion property. The first one is the following. If we had L1 prime, the largest component before sprinkling, it looks a little bit ugly. It's a last minute change indeed. And there is this L1, our target largest component. But if you look at every component, which is in L1 minus L1 prime, so you just delete L1 prime from the L1, then it consists of only small components of order D, and most D. Yeah, so I just try to depict with bright gray bubbles. Of course, there are also connections between them, but nevertheless, they are all small. Yeah, these are small, and most D, and so on. So L1 minus L1 prime is just consisting of small components. Furthermore, if you look at any vertex in the original hypercube, yeah, without population, yeah, any vertex in the original hypercube, then this is within distance and most 2 from the L1 prime. So I also try to depict not only in L1, but everywhere, yeah, L1. Every vertex in the original hypercube is within distance and most 2, yeah, within distance 2, sorry. So at distance and most 2, at distance and most 2, and most 2, but also there are plenty of them indeed. So within distance 2 from at least this square many vertices in the giant component L1 prime. Yeah, of course, L1 prime is of order T to the D. So from that point of view, this square is not many, but nevertheless, we are aiming for expansion property of the polynomial in D. So it's a kind of a very useful thing to have. Yeah? These are the two ingredients. Then having this is as a pre-processing, we have this information in mind, but then what we do is the following. We split the giant component before sprinkling into a family of vertex disjoint connected subgraphs. We call these big bubbles as PCs. We just chop them up. Vertex disjoint connected subgraphs of size less polynomial of D, polynomial in D. Indeed, it will be about between D and D squared up to some factors, yeah, between D and D squared, but let's say poly D. Just call them PCs. We split L1 prime, the vertex set of L1 prime, not a vertex set on the but everything indeed, yeah, the L1 prime into small PCs. Sondern was German indeed. So and then we know that L1 is a union of oops, there is some typo, that's Q1 and Q2, yeah, so sorry for this typo. L1 was the original giant component, and if I see the whole picture, it was like that, yeah, something like this. And next, we want to study the vertex expansion property. So we have to take an arbitrary subset of the vertex set of the largest component L1. So we take it as S, an arbitrary subset of the vertex set of the giant. Then of course, this meets L1 prime and L1 with a different manner in view of these small pieces. Yeah, indeed, we can characterize, or we can partition S into three classes. Indeed, this is this blue bubbles into three classes. Namely, the first one, S1, will be those that do not lie in L1 prime. Yeah, namely, set S is a subset of a L1, a vertex set of the L1, but it is outside of the L1 prime. Yeah? It's colored in a dark blue here, these bubbles. They either covered entirely disconnected component or just partially, it doesn't matter. Second class is S2, which are the vertices in the PCs. Yeah, these big bubbles, PCs. But it intersects partially with each piece, partially like that. Yeah, so it intersects with the PCs, but not completely, fully contained in it. So we color it by light blue. But then there are other vertices in PCs, but they are fully contained in such PCs. Yeah, so once again, so we had this arbitrary subset, and we split S into three classes depending on how it intersects with L1 prime and L1 in terms of the PCs as well. Yeah? So this is the three classes, and we will measure the contribution of S1, S2, and 3 to the external neighbor separately. Still have time, yeah. So for the contribution of S1, I just copy the picture, same picture here, and make it a little bit smaller. This sprinkling edges, the second exposure, will help us a lot. Namely, with this sprinkling, I just make it as a red. It's very easy to see by per definition that each component in L1 minus L1 prime is with gray bubbles, which intersect with S1, this darker blue, would contribute at least one edge to the external neighbor of S, namely like that. What is this one? This is not this one, yeah, like external. This has nothing to do with S. So this is indeed external neighbor of S. So either it contribute one edge to the external neighbor. If it was not there, then this also external neighbor. So either it is not either. Sometimes it can be both, but anyway, contribute at least one edge to to the external neighbor, it's either or. Indeed, it's either contribute at least one edge, like here, or it is connected to green, namely F3. Those are completely contained in the piece, or partially, like here. Yeah. The picture says everything, but picture is rather complicated. So once again, with the sprinkled edges, each component in L1 minus L1 prime, which intersects with S1 with the blue, contribute either at least one edge to the external neighbor of S, or it is connected to S2 union S3. Just the easy counting says that indeed the size of the NS therefore will be some constant times the size of S1 divided by D divided by B, because we do have these small bubbles either of size M mod D, or we have a D regular, so we have to divide by whatever possible, or the edges between S1 and S2 union S3 is of the similar type, and also because our bubbles are small, or we are in D regular, using that simple fact, we can also know what should be the cardinality. So cardinality of the size of the S2 union S3 is large. So either the external neighbor of S is large, or S2 union S3 is large. It's a little bit of case distinction. So this is the contribution of S1. And contribution of S2 is rather simple. So S2 was the vertices that partially intersect with the pieces, yeah, these big bubbles. So this gray, so light blue bubbles, we want to look at its contribution. Then it contributes at least one edge to its external neighbor, independent of how it does it look, yeah, by definition indeed. And then just also easy thing is that size of the external neighbor should be at least the size of S2 divided by poly D, because each piece is now of size of poly D. The way we chopped or split our L1 prime into smaller pieces was exactly that each piece is of order polynomial in D. Yeah. If you want to have a better and better results, but at some point you have to optimize this poly D, and our optimization was between D and D square almost. Yeah. So indeed, previously we had some other factors, but then we try to optimize it, and this is it. The most complicated contribution comes from S3. Yeah, how much does this pieces, vertices in pieces that are fully contained in each pieces contribute? To measure that, we will partition the class C, so these bubbles, into families A and B. Yeah, the whole C are all these gray bubbles into two classes. Namely, A will be the pieces that are fully contained S, namely these green ones, and the rest. Then, of course, that partition also induce or leads to partition of the vertex set of the L1 prime, namely those that are contained in A, namely they are identical to S3, because those are the vertices that are fully contained in S, and the rest. Yeah. Why this is helpful now is the following. We can indeed extend the partition of L1 prime into larger partition of the whole cube. Yeah, now forget about yet this bond population. So L1 exists, L1 prime, and then the whole cube before population. Partition, we can extend to it the partition of the whole cube, so that every vertex, so A bar and B bar, so A bar contains A partition class of L1 prime, such that every vertex in A bar is within distance to A. Likewise, our B consists of such vertices that were covered in S2, and the others, whatever they are also within distance to B. So we classify this way using this distance 2 thing, and we have seen that ingredient already before, right? This is exactly where we need this fact about these distances that I have shown you as a pre-processing. Now, why this is useful is the following: using Harper's edge isoperimetry inequalities, among other things, one can show that indeed there is a big matching between A bar and B bar. It looks like a perfect matching, but it's not. It's a large matching. And after sprinkling with this very tiny probability, delta 2 over D, nevertheless, large proportion of them that are large, meaning that for our purpose large, survives. Yeah, these red things. Because of the bird matching, indeed, it is like a path of length 5. Yeah, so in other words, after sprinkling in the random subgraph, there exist at least then many. So cardinality of A divided by poly D is also poly D has to do with all these pieces, size of the pieces, nevertheless, but different polynomial. Vertex disjoint paths from A to B of length and most 5 after the percolation. It helps then a lot. Then using that, so you have to just read it. What is the effect? What we want to count now was the contribution of S3. This was identical to A. So each such path, AB path, will contribute at least one edge to the external neighbor of N over S. We want to look at what is the contribution of the external edges, external neighbor of that green guy is, and indeed you see at least one of such popping out outside of the A, and therefore the size of the external neighbor is at least the size of that 3 of poly D. Apart from those, it goes to this light blue. This was S2, so you have to subtract. So we can wrap up what we have shown. This is just arithmetic now. We have shown either or, either or, either or. So what you do, you just do the case distinction, and you can do this easily. In every case, it yields the neighborhood of external neighborhood of S is at least cardinality of S divided by poly D. And if you choose these parameters, I just hide all these poly D things carefully, then you can obtain what I promise, this kind of the expansion ratios, which is very, very, very good indeed. And as consequences, these nice properties. Of course, having those results, it kind of very natural to ask whether we can do it better. Yeah, we can do this. Can we improve this one? By improving that, we will improve that one. And can we do better with that? Can we do better with everything? Yeah, so this is my open questions. Can we do better? Can we obtain the best possible, what we believe it to be the optimal? Yeah, thank you very much for your attention.
If anyone have any question, you can unmute yourself and ask question.
Can you say something about the second largest component?
Second largest component is of order big O of D. Yeah, but structure, we don't know yet.
Okay.
In terms of the largest, the second largest is all very well known, even not only the supercritical, but so-called weakly supercritical and also the barely supercritical, in particular by probabilists like Van der Hofstad, Box, Christian Box, Jennifer Chayes, Spencer, Nachmias. Yeah, all this.
Is there other random subgraph model, like random regular subgraph or random other subgraph?
Oh yes, yes. Random subgraph is very general concept. Given any graph G, which is deterministic or random, you can always go through the so-called bond population. For the regular graph, if you do the bond population, so random subgraph over the regular graph, then it will be like a random graph with a given degree sequence. And this has been proved already by Janssen and Fantolakis independently. It's a beautiful theorem. So basically it boils down to random graphs with given degree sequence. Yeah, because of the fluctuation. Huh? Yeah.
Any other question? If not, let's take a again.
Thank you very much.